In this video, we're going to go through the questions on scalars and vectors together, and we are going through 4 questions from the easy questions. As usual, I would recommend you have a go at these first and then use the video, pause and play it, use it to mark your work or use it to help you get the answer. Okay, question 1. Explain the difference between scalar and vector quantities. So a vector has size, which is sometimes called magnitude, and a direction, whereas a scalar quantity has only a size. It is not specified which direction it will be in. Question 1b, table 1 contains a number of scalar and vector quantities. Place 1 tick in each row to show whether each quantity is a scalar or a vector. So speed is a scalar, velocity is a vector, mass is a scalar, weight is a vector, distance is a scalar, and displacement is a vector. Question 1c. Figure 1 shows a uniform beam supported by 2 light cables, AB and AC, which are attached to a single steel cable from a crane. The beam is stationary and in equilibrium. State 2 reasons that the beam can be described as in equilibrium. So that means it's not moving. And so we're going to say it's 2 marks, so we're going to give 2 points. We'll say all the forces are balanced. And for our second point, we will say that means the beam isn't moving. We will do more questions similar to this in a later topic after we've done scalars and vectors. Coming on to question 1d. Actually, I'm going to put it there because we're going to need that diagram. The cable in the tension AB is 3 newtons, so I'm going to label that. AB is 3 newtons, and across AC is 4 newtons. Calculate the resultant force required in beam BC to keep the system in equilibrium. That is this one here. So we're going to use Pythagoras' theorem for that. So 3 squared plus 4 squared. And if you type that into your calculator, 3 squared plus 4 squared, you will get 25. But if I just quickly remind you of Pythagoras' theorem, we've got our square, we've got our triangle here, A, B and C. A squared plus B squared equals C squared. What we've just worked out here is C squared, and we actually just want C. So what we're going to do is we're going to square root our answer. Square root of 25 equals 5 newtons. So that is our final answer. 5 newtons is needed across the bottom there to keep our beam in balance. On to question 2a, state 2 vector quantities and 2 scalar quantities. So you can use the ones from the previous question or some other ones. So for example, for our vector quantities, we've got velocity, acceleration, or displacement. You could have also had force or weight there. And for scalar, we could put speed, distance, or mass. Any of those would have got you the answer. 2 vector and 2 scalar. On to 2b. The helicopter shown in figure 1 is moving horizontally through still air. The lift force from the helicopter blades is labelled A. Name forces B and C on the helicopter. So we haven't gone over this yet in AS level, but you should hopefully remember it from year 11 physics. C, the force going down, is going to be our weight. So that's mass times the gravity, and B is going to be our drag or air resistance. Question 2c. Our helicopter is moving at a constant velocity. So if it's going at a constant velocity, that means that the forces are balanced. We will learn a little bit more about that in a later topic. Draw a force vector triangle to show this arrangement. So you'll want to flick back, have a look at figure 1 and try and work out how you can draw those arrows so that A is your resultant force and B and C are at a right angle. So you're going to have B going across the top, C going down. If you have a look at figure 1, they're in exactly the same direction that they were a minute ago. And then A, our resultant force, is going to come diagonally up. That would get you both of those 2 marks. Having a look at 2D, force B has a value of 25 kilonewtons and force C has a value of 40 kilonewtons. Calculate the value of force A to keep it going at a constant velocity. So what force do we need to balance those 2 out? So we need to work out our resultant force. So again, we're going to use that Pythagoras rule, but we're going to do B squared plus C squared, and we're going to square root it to get A. So A is going to be equal to the square root of B squared plus C squared. The numbers we are going to put in are going to be 25 squared plus 40 squared. Do not forget to square it and then to square root it at the end, and you will get A equals 47.17. Our question tends to use 2 significant figures, so we will round it to 47, and it is in kilonewtons, so don't forget to put that K before you put your N for newtons. Question 3a, what is a vector quantity, and give 1 example. So we've already done that right at the beginning, but it's just to keep it going through your mind. So it has both magnitude and it has direction. So that will give you a first mark, there's your definition. And for our example this time, let's go for velocity, the easiest one to remember. Question 3b. Figure 1 shows a ball suspended from a cable. The ball is pulled into the position shown by a rope that is kept horizontal, and it is in equilibrium. Equilibrium, so it's not moving, all the forces balance. State the force and component which will balance the force of the rope on the ball and the weight of the ball. So if we have a look at this one, that is going horizontally towards the left. So what we need is a force going horizontally towards the right. So to get your mark here, all you would need to say is it's the cable, but the horizontal component of the cable. If you remember when we were resolving vectors or resolving forces in class, we can break down that T2 into a horizontal component and a vertical component. So it's just the horizontal component of the cable that balances out the rope. However, for the weight, it's going to be the cable again, but the vertical component. Personally, I think that sort of question is easier when it actually gives you numbers. All that is doing is checking that you understand that T2 from the cable can be broken into a horizontal force and a vertical force, and that is what is balancing out both of our other forces. Question 3c. When it's in equilibrium, the tension T1 is equal to 10.1 newtons and the tension T2 is equal to 15.7 newtons. Calculate the weight of the ball. So this question is a little bit challenging, that is why I have given you a hint. So T2 is the resultant force of T1 and W. Use Pythagoras but rearrange it. So I will draw the triangle because that will help us understand what we're going to do next. So we've got our weight going down, T1 going across, and T2 is our resultant up there. So usually we'd use Pythagoras to work out T2. T2 squared is equal to T1 squared plus W squared. But instead it is asking us to calculate the weight, so we need to rearrange. So if I want the weight by itself, I'm going to have to take away T1 from both sides. So what I'd actually type into my calculator to work out the weight is the square root of T2 squared. Let's have a look what that is. 15.7 squared. Take away the square root of 10.1. So I've just put that in brackets so I don't get any issues with my negative sign. And the answer that you would get there for your weight is 12.02 newtons. The question is mostly in 3 significant figures, so we will round that to 12.0. We put that 0.0 just to show that we have rounded it to 3 significant figures, not just to 2, and the answer is in newtons. Question 3D. So the ball is detached from the rope, now it is only hanging by the cable. State the new tension. So we're going to use our answer from the previous question. We found out that the weight is 12.0 newtons. And if that's our only vertical component and the cable is balancing it out, that means that the new tension, T2, must also be equal to 12.0 newtons. So whatever you put in the previous question. On to 4A. Decide whether these are vector or scalar and what's the unit. So force is a vector, displacement is a vector, and the last two are scalar quantities. Force is measured in newtons, N. Displacement, similar to distance, but distance would be your scalar one. It's measured in meters, or in M. Kinetic energy is measured in joules, and power is measured in watts. It does say give the full name, so I will write those in. Newtons, meters, joules, and watts. Onto the final page of our booklet, we're going to be looking at times that you can draw things to scale instead of using mathematics to work out the answers. So figure 1 shows two forces acting on an object O and the forces have been drawn to scale. State the scale that has been used in figure 1. So I don't know if this is going to print out to size, but each one of these should be 1 centimetres. So what we're going to do is we're going to use the 2.31 here and we're going to measure how long it is. So you can either use a ruler if it's printed out correctly, or if not, we can just count the squares. 1, 2, 3, 4, 5, 6. I'd say it's just over half there. So let's say it's 6.6 squares or 6.6 centimetres. So we're going to work out how many newtons does each centimetre represent. So to that, we're going to take our 2.3 newtons and divide it by 6.6 centimetres. And you're going to end up with 0.348 newtons per centimetre. And we might as well round that to a more sensible number, 0.35 newtons per centimetre. So that is the scale that they've used in the diagram above. Yours might be a little bit different depending if you use 6.6 or 6.5 or 6.7. 4C, complete the scale drawing to determine the magnitude of the resultant force. So I've given you a hint here because I don't usually draw these to scale. I usually just use maths to get the answer, but you should be aware of roughly how we're going to make this into our triangle. So we need to draw a parallelogram, and to do that we're just going to copy this line here. We're going to pop it on the end of here. So if I have a look, it's roughly 2 and a bit squares across, 1, 2 and a little bit. That's about that height. So it's not going to be perfect unless you want to get out your protractor and have a go. So that is our parallelogram. So the lines across here should be parallel. These ones should roughly be parallel. Then we're going to draw our resultant force. So instead we're going to put our 1.8 newtons over here. And then we just draw our, I'll use a different colour, draw our triangle as normal. This is our resultant force. I'm going to label it R. Then you would measure the length of it. So roughly the length of this should be, if it prints out correctly, 6 centimetres. I'll write that here. Length equals 6 centimetres. And then we just times it by our scale off the one above, times 0.35, and you're going to get 2.1. Don't worry too much if you didn't follow that one. In the Welsh exam board, we can only ask you questions where there is a right angled triangle, rather than up here there is no right angle. So any time that you will be doing this will be simpler than this example. And finally 4D, one that is definitely achievable for you because we put our right angles back in. So instead this time our 1.8 Newton force is going to act vertically upwards. 1.8 newtons. And across we've still got our 2.3 newtons. And we could calculate our resultant force here, but it doesn't want us to. It actually wants the angle here. So we're going to use our trigonometry, which is the tan of the angle is equal to the opposite over the adjacent. If I remind you, opposite our angle, adjacent is the one between the angle and the right angle. And this is our hypotenuse. We're not going to use our hypotenuse because we've not worked it out yet. So the tan of the angle would be the opposite divided by the adjacent, but I want just the angle. So I'm going to do the tan minus 1 of the opposite, which is 1.8, divided by 2.3, our adjacent. Type that into my calculator and I should get 38 degrees. So make sure you've had a good go at all of these questions or marked any that you have already done, and feel free to come to me in school if you have any questions about any of these and we will go through them.